Dear students, today we'll see the very important topic, the classes of power amplifiers. So the classes of power amplifier are classified according to the percentage of time the output transistors are conducting or which is turned on. So you can see here in this figure clearly the class A amplifier is conducting for 360 degree 360 degree, right? So that means your your class A amplifier will be on for throughout the region, throughout the positive swing or negative swing. Class A amplifier will be on. When you go for a class B, it will be on only for 180 degree, the only for positive signal, similarly for negative signal with respect to the device. So the remaining part of the signal, your transistor is not on, right? It will be in off condition. So that you want to understand, very important. When you go for a class AB, so you can see here your A is working in 360 degree and B is working in 180 degree, and class AB will be working greater than 180 degree and lesser than 360 degree and equal to 270 degree. That means you want to understand like a your there is a here the understand said clearly the classified according to the percent of time the output transistor are conducting. So that is the turned on time, right? So that is very important. So other you have other amplifiers also, class C and class D to T. So those will not come under the classification of amplifiers. Those will be used for some other tuning application and some switching application. We are not going to discuss those topics. So we will be covering class A, class B and class AB, right? So here you can see here you can the class A amplifier you will be working for 360 degree, right? You will be working for 360 degree, and class B it will work for 180 degree and class AB will work for 270 degree. That means, so you can understand very clearly. So you consider your output characteristics, that is your IC versus your VC. So it is MOSFET, right? So it should be a ID versus VDS. So this is a load line, and so if you want to have a like a class A amplifier, your output transistor is biased at the quotient point and conduct the full entire cycle of the input signal. That means you should choose your quotient point exactly in the central region of your like a non-saturation region and the saturation region, right? Dear students, today we'll see the important topic, the classes of power amplifier. So you know that we will be studying the two type of amplifiers, small signal amplifier and power amplifier. So when you speak about the power amplifier, the power handling capacity of those transistor will be larger compared to the small signal transistor. So the power amplifier able to handle more than 1 watts. Okay, so correspondingly the spec values will be differ based on your the transistor uh, parameters. Okay, so here what you want to understand is how the classes of our amplifiers are classified. So here how they are separated is actually according to according to the percent of time the output transistors are conducting or turned on. So you can see clearly according to the percent of time the output transistor are conducting or turned on. So when you see class A, it is conducting for 360 degrees. When you see class B, it is conducting for 180 degree. When you see class AB, it is conducting greater than 180 and lesser than 360 degree. So the approximately 270 degree. So we have other amplifiers also, like we are discussing dominantly like A, B and B amplifier. We will not touch other amplifiers like a C, D up to T are having. So those amplifiers will not work on the principle of amplifier. So the circuits are used for like a tuning application or some other switching application. So we are concentrate only for the amplifier part, like a B and AB power amplifiers. Okay. So when you go for class A, see, read that sentence, you will be understanding clearly the output transistors. The output transistor is biased at the quotient current IQ and conduct the entire cycle of the input signal. So what they're saying is the output of your class A amplifier will be a full entire cycle of your input signal. That is an amplified version of your input. So that means, see, consider your MOSFET. So that is enhancement MOSFET. Your output current will be ID and output voltage will be VDS. So this is your output response, right? This is your output response you will be getting after your DC biasing, right? So here when you draw the load line, this will be your VDS, like this will be a, so this is a ohmic region and this is your saturation region. This is the region at which your transistor is moving from their ohmic region to saturation region. That region we used to say VDS saturation equal to VGS minus VTM. Understood or not? So it is a point called transition point at between your saturation region and non-saturation region. This is the minimum point at which the swing will be starting to flow. So this is a quotient point that you are expected to fix. This is your upper end of your line. So you can see the full swing without any non-linear distortion. So that means your output, your transistor is operating for the entire cycle of the input signal. So this is a class A amplifier. When you go for class B amplifier, the output transistor will conduct only one half of your each sine wave input signal. That means when you draw your response, that is output characteristics VDS. So I will be fixing your quotient point in the cutoff region. So that means you will be getting only one half of your signal. So other half of the signal will be clipped out. So basically you want to modify the circuit to get your full swing. So with the one device you will be getting, like in the class B, with the one device you will be getting a one positive swing. Similarly you want to add the another complementary device in the downside to get the another part of the signal. That we will discuss in the coming slides. Okay, so what you want to understand is the class A will be conducting for full 360 degree signal or your input. And class B will be conducting only for the 180 degree signal with respect to the input part. When you go for the class AB, you will be fixing your the quotient point less than your cutoff region. That means the transistor will conduct slightly more than your cutoff, like a half of your cycle. So that means you can understand. So you will be fixing the quotient point here, right? So your output will be something like this. So you can see it is greater than half of the cycle but lesser than the full output cycle. Okay, so when you final observation is the class A amplifier is working for 360 degree signal and class B amplifier is working for 180 degree signal and class AB is working for 270 degree signal approximately. So this is the thing you want to understand. The basic thing is the classification of power amplifiers are classified based on the present of time the output transistor are conducting or turned on. Based on that only the classifications or power amplifiers are differentiated, and here comes the value of fixing the quotient point. When you want to have a full swing, it should be in the center of your like your ohmic region and the cutoff region, right? So that is your saturation region. So when you want to have a like half of the part signal, you want to fix in your cutoff region. When you want to have more than half of a signal, you want to fix less than your cutoff region. So that's what we learned, right? Okay. So like a same I was explaining you the class B amplifier, the class A amplifier, you can see you are getting the full swing. The class B you can see you are getting only 180-degree signal, and class B is greater than 180-degree but less than your 360-degree signal. Okay, so in that way it will power amplifiers are classified. So now very important and challenging question is, we will start with the class A amplifier. We will start with the class A amplifier, and important question here is, so class A amplifier will conduct for 360-degree signal, you know clearly, but the efficiency is very poor. So the class A amplifiers will not prefer for most of the application. Why? That you want to understand. So very simple, the class A amplifier, the transistor is biased such that the output current flows, the transistor is on. See, very important point, the transistor is on for full cycle of your input AC signal. That means for the both the positive and the negative swing, your transistor will be on. The output device is always on, right? The output device is always on at all the times, and it consistently carrying the current, which represent that you have a continuous loss of power in the amplifier. So another thing you want to understand is, if you have a continuous loss of power in the class A amplifiers, the tremendous amount of power will be released near in and around. So based on the heat, so tremendously reduce your efficiency in your device. Okay, the performance of the device will be reduced. So the performance of the device will be designed based on your efficiency of your device. So due to the huge losses of power, the class A amplifier is giving the less efficiency. The reason is very simple. The transistor will be on for both positive swing and negative swing. So the throughout the period of the input signal, it is on. So the power wastage also will be more. In that consideration, your power amplifier, class A amplifier efficiency will be very less compared to other power amplifiers. Approximately your efficiency will be varying from even 5 to 30 percentage. Okay, that based on the design. So efficiency will vary from like a maximum efficiency of in and around 25% to 30%. So that is up to the based on your designing part. Okay, so I said clearly the class A amplifier like will not prefer for most of the application. Like it is preferred only for very some selected application. Like if I want to highlight the one of the application is your outdoor musical system. Okay, so there like your class A amplifier will produce a full 360-degree like a sound. So that means it is producing a sound is very clear and more linear, right? But problem with the class A is due to the higher exhaust amount of heat, that will reduce your efficiency drastically. So most of the application the class A amplifier will not be used. Okay, only for some like a rarely accepted in some home applications. Okay, so because of the low efficiency, and the low efficiency is because of the huge amount of power loss. The power loss will will proportional to the temperature generation, that is a heat generation. The heat generation is more, obviously the device performance is going to reduce drastically, that you want to understand. So the final conclusion observation is efficiency is very poor, right? Efficiency is very poor. If I want to say what is the advantage of your class A devices, your output signal will be a replica of your input signal, right? The output signal will be replica of your input signal. Output will be exact replica of input signal. So device is on for all time, so you don't have a crossover distortion. That is one advantage. No crossover distortion in your class A amplifier. But the major drawback is it like a its circuit become very bulky and large, and efficiency was very poor. Okay, so that's why the class A amplifier will not be preferred for most of the application. Only for selected application class A amplifier will be preferred. Okay, now we are going to see what is the efficiency, that is a power conversion efficiency of the class A amplifier with some mathematical equation. So here you can see this is your class A amplifier circuit. So this is your gate and this is your drain and this is your source. The source is connected to the earth, that means it's a common source circuit phenomena. So in the gate your VA you are applying, right? So the RD is your output resistor and the corresponding current is ID, and VDD is your DC supply voltage. Okay, when input is 0, please understand, when input is 0, when I'm applying VA is 0, you will be having the DC quotient point, right? So DC quotient point will be generated and will be fixed. So then only you will be applying your you're superimposing your AC signal in your circuit, right? So here you can see that is your ID versus VDS. So this is your quotient point which you fix when you consider VA is 0 and you fix this quotient point, that is your VDSQ and IDQ. So you have a corresponding formula, that is your design formula, that we will see in the coming slides. Okay, there is a formula for VDSQ and IDQ also, that we will see in the coming slides. So when you choose the operating point exactly in the center of your cutoff region and the ohmic region, that is, you can see you have a full swing, right? You can see this was a full swing that is produced of this fixed operating point. Okay, so here very important is the transistor is moving from the non-saturation region to saturation region at the transition point. So that condition is, we used to say, that is a VDS saturation. So it is a point at which your ohmic region, that is a non-saturation region, is entering to the saturation region. That specific point is called transition point, that we used to say as VDS saturation equal to VGS minus VTN. So it is greater than or equal to VGS minus VTN. It is a point at which your transistor is entering to the saturation region. So the corresponding condition is VDS saturation equal to VGS minus VTN. Right. So the other required equation, you can see the output voltage. How you can find your output DC voltage? So very simple, apply the KVL across your output loop. Okay, when you apply the KVL across the output loop, so this is your plus and this is your minus. So apply like this, anti-clockwise direction. So what you will get, plus VDD, then this entering at a plus, leaving at a minus, so minus IDRD, so entering at a plus, leaving at a minus, so minus VDS equal to 0. So when you rewrite this formula, VDS equal to VDD minus IDRD. So this is the formula they have written. Okay, this is the output DC voltage, so that is VDS equal to VD minus IDRD. So ID we can obtain from this equation, that is your drain current equation, ID equal to Kn VGS minus VTN whole square. Okay, when you combine this equation, that we know that already I said. So this is a point, you can see this is a minimum swing. Okay, when you are finding for non-linear distortion, non-linear amplification, right, you will be having a swing from your, say I will erase it. So you will be this is a point. So consider this is your somewhere the transition point. Okay, so here only the swing will be starting. Okay, so this is your quotient point and this is your maximum swing. Okay, here only swing will it is the best range to get the linear amplification. To get the non-linear amplification, this is the range to be maintained. So it start from the VDS point and end it at a maximum of VDD. Okay, that you can see clearly. So like I'm taking this equation in terms of minimum point, that is a VDS saturation. So this VDS I'm just customizing as VDS saturation to find the minimum point. Okay, so VDD minus what is your ID? ID is Kn VGS minus VTN. So what is your VGS minus VTN? That is nothing but your VDS saturation. So that when you apply here, you will be getting V square ds. Okay, so when you substituting this ID here, this equation was rewritten like this. Okay, so you can understand clearly. So I explained you, that is VDD minus IDRD. In the ID, you have a Kn VGS minus VTN whole square. So VGS minus VTN is nothing but your VDS. So here you have a square, so it was written like V square ds saturation. So in that case, this formula was updated. Okay, now we are going to derive what is your conversion efficiency, power efficiency. So I said clearly efficiency will be in the range of 25 to 35, like a maximum. The minimum it can be like a 10, 12, 13, 14. That is based on the design. Okay, so when you see the formula for conversion efficiency, you know the conversion efficiency formula. That is your load power divided by source power. Source power means that is your average power supplied by your DC source, by your source VDD. That is the average power. I am repeating again, average power supplied by the source, that is your DC source. Load power means average AC power to the load, average AC power to the load. Okay, that is when you find the ratio of PL by PS, you can find your conversion efficiency. Okay, so first we will see what is your PS. The PS, you know, that is your average power supplied by your VDD. So what you will get, that is your VDD into ID cube. That is a product of your applied voltage into your generated quotient current. So that is VDD into ID cube. So that is your source power formula. Now let me go for your with respect to the for sinusoidal input signal. So what is the average AC power delivered to the load? That is the formula. So the repeating again, what you want to find is what is the average AC power delivered to the load. So you know that the formula for power, so that is we can write like a V into I. So that I can customize with respect to the like a sinusoidal signal, that is the AC power. So I can write like a IRMS. So with respect to the sinusoidal signal. So I can write with respect to the sinusoidal, VRMS can be write like a Vm by root 2 and Im into root 2. When you multiply, you will be getting 1 by 2. So I can write Vm as a Vp. So both are same. So Im as a Ip. So from this I can change this Ip. You know the Ohm's law. So it's a powerful law. V equal to IR. So I want to find what is I. So that means V by R. So I can write like this, right? So I can write like a Vp by R. Can write like a Vp by R. Okay. So I can write like a Vp by RD. Your output resistance is RD, right? So here you have output resistance RD. So that it was included. With that you can see Vp into Vp, that is V square P divided by RD into 1 by 2. So in that consideration only this formula was derived, and this is a formula for like a drain current. Already you know IDQ is nothing but your Kn into VGS minus VTN by whole square. So from your output equation also I can like a VDD minus IDRD. So both answer is going to be same anyway. This is another way of representation. So when you find ID, so I can write like a VDD minus VDS by RD. So this is a formula for finding your ID. Right. So now thing is, you know what is your PS? The PS is nothing but your VDD into IDQ. That is the average power delivered from your supply voltage VDD. Right. So when you find your load power, that is the average AC power, average power, like average AC power to the load, average AC power to the load. So in terms of peak voltage, we should write. So that it is written as 1 by 2 Vp by Vp into Ip. That is a peak voltage into peak current. So you can see from here the peak voltage will be something like a peak voltage and peak current will be something VTD IDQ by 2. So the maximum AC power delivered to the load will be VDD IDQ by 2. Okay, when you substitute here, already you have 1 by 2. So you will be having VDD IDQ by 4. So when you, what is the formula? So VDD IDQ by 4, what is your PS? VDD into IDQ. So both will be cancel and you will be having 1 by 4. So 1 by 4 in terms of percentage, you multiply by 100, you will be getting 25%. Okay, that is approximately here it was given. Right, approximately it was given here.